mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Before we get going today, I thought I'd start today with our verse of the day. And our verse of the day today comes from Psalm 24. And the verse of the day that came to me was Psalm 24, verse 10. But I think in order to put that into context, I'm also going to read Psalm 24, verses 1 and 2. So, Psalm 24, verses 1 and 2 say, "The earth is the Lord's, and everything in it, the world and all who live in it. For he founded it upon the seas and established it on the waters." And then going on into verse 10, it says, "Who is he, this King of glory? The Lord Almighty. He is the King of glory." So, as we go through the day today, we want to reflect and remember that Jesus is the King of kings and the Lord of lords. He is the King of glory and our Savior. We thank him for that. All right. Good morning. So yesterday you had an assignment that included a bunch of questions on conservation of energy. And today all I want to do is go over a few questions. I'm not going to give you any new content today. At the end of today's lesson, you'll be able to find another assignment on Connect and just some more practice before we move on. And so going over yesterday's questions, first thing, question number 1. So question number 1 had a diver on a 12-meter platform jumping off with no vertical velocity, first of all, and then falling the 12 meters. And the question was simply, with what velocity will this diver hit the water or the ground? And so to do this, we want to again look at energy, okay? What kinds of energy do we have at each point in this question? And so we start at point A up top here. At point A, the diver is off the ground, so they have gravitational potential energy. They are not imparting any vertical velocity, and so they don't have any kinetic energy at that point, and there's no springs involved in this question, so there's no elastic energy. So at point A, there is only gravitational potential energy. When we get down to the bottom, we'll call that point B. At point B, they are now no longer off the ground, so they have no gravitational energy. They will only have kinetic energy. They'll be moving with a speed when they hit the ground. And so what that means is when we set up our conservation of energy formula, which is E total equals E total, okay? We're going to have the E total at point A equaling the total energy at point B, which means the gravitational energy from point A has to equal the kinetic energy from point B. mgh equals a half mv squared. Mass doesn't change, so it can cancel out, leaving us with 9.8 newtons per kilogram times 12 meters equaling a half v squared. And if we rearrange that to solve for v, we will get 15.3 meters per second. Now in part B, there's only one small change. In part B, this diver now does impart a vertical velocity to start. So that means at point A here now, they have some kinetic energy because they're moving upwards. And they have gravitational energy because they are still off the ground. The bottom doesn't change because they are no longer off the ground, which means no gravitational potential, and they're moving, so they'll have kinetic energy. So again, when we set up our formula, E total from A has to equal E total from B. EG plus EK from A has to equal EK from B. Again, we plug in our formulas. We see that the mass cancels out because there's mass in each term. And we plug in our values, and when we solve for V, we'll get a value of 16 meters per second. This is the kind of thing we will do in each question. It will always be an E total equaling an E total, and it's just filling in the appropriate formulas to solve for the quantity that's required. And so we're going to continue doing that. We've got example number, or question number 2 on the board next to me here. Okay, here's question number 2. So question number 2 has a high jumper jumping over a bar. All right, and so it tells us that the bar is 2 meters above the ground. We want to know with what velocity this jumper needs to leave the ground to get their center of mass above that 2 meter bar. We're just going to say it's exactly 2 meters. All right, so question tells us the center of mass starts 0.85 meters above the ground, which means it has to go up 1.15 meters in order to clear the bar. So again, if we look at point A being at the bottom here, point B at the top, at point A, this jumper has kinetic energy only. We're going to take their starting point as 0 for height above the ground. We could put it as 0.85, but then we're going to put it onto both sides of the equation. It's going to end up canceling out. With gravitational energy, we just need to look at the change in gravitational energy, and so that height is changing 1.15 meters. So again, we're going to set up our E total from point A, which is at the beginning of the question, to E total at point B, which will be at the highest point that this jumper gets. And again, at A, if we take that as the 0 height, we're going to have just kinetic energy, the velocity with which this jumper needs to leave the ground, and we're going to equal to the gravitational energy when they get to their highest point, which again, at their highest point, they vertically stop moving, which means they'll have no vertical kinetic energy before they start going back down. 1/2 mv squared then has to equal mgh. Mass cancels out once again, and we're left with 1/2 v squared equaling our 9.8 newtons per kilogram times the 1.15 meters. That's again the height that will change, right? We're going from 0.85 up to 2 meters, a change in 1.15. Solving for v, we get 4.7 meters per second. We're going to continue. Question 3. All right, for question number 3, I'm not going to draw it out. We're just going to do it together at this point. We have what do we have for question 3? A 2 kilogram mass. It's placed against a spring with a force constant of 800 Newton meters, and it's been compressed 0.22 meters. The spring is released, and the object then moves along a horizontal, frictionless surface and then up a slope. And it breaks it into a couple of different questions for us. So part A simply says, what is the maximum elastic potential energy of the spring? Well, that's fairly simple. We have a formula for elastic energy. So if we're looking at question 3, part A, we know that elastic energy is equal to 1/2 kx squared. And we know that the force constant is 800 newtons per meter, and that it is compressed 0.22 meters squared, giving us a maximum elastic potential energy of 19.4 joules. Okay, 19 as the textbook would say. All right, part B of the question says, what will be the maximum velocity of the spring? Now, here's where you have to use a little bit of physics knowledge. Where will this spring reach its maximum velocity? Well, or the block reach its maximum velocity? Well, it'll be at its maximum velocity while on that horizontal part. Now, it's frictionless, so it's not going to change in that. So as soon as the spring is fully extended, the block leaves the spring, it's at its maximum velocity. So in other words, at that point, all the elastic potential energy has been converted into kinetic energy. And so that's what we need to do. This 19.4 joules has to equal the kinetic energy of the block once the block leaves the spring, and the spring is no longer compressed at that point. So our kinetic energy of the block has to equal 19.4 joules, and our kinetic energy is 1/2 mv squared. And so we have a 2 kilogram block, and we want to solve for the velocity. And so when we do this, we get the velocity equal to the square root of 19.4, which is 4.4 meters per second. All right, so again, we're looking at that. Now, part C asks us what maximum height does this reach going up a slope? Well, now, when it goes up a slope, it's going to get to a height and it's going to stop. That'll be its maximum height. At that point, the block will only have gravitational energy. The spring's not compressed anymore, it's no longer moving, so it doesn't have any elastic potential, it doesn't have any kinetic energy, it only has gravitational energy. So for part C, this 19.4 joules, which is conserved, gets converted all of it gets converted into gravitational potential energy. And so for part C, we're going to say, well, now the gravitational energy equals 19.4 joules. Gravitational potential energy is mgh equals 19.4 joules. Let's plug our numbers in. You can still see this. We have a mass of 2 kilograms, a G of 9.8 newtons per kilogram. The height is what we're looking for, and it equals to 19.4 joules. And if we solve for that, I'll put the height over here. The height will equal to 0.99 or 1 meter. And again, we're looking at this. We are looking at conservation of energy. We had 19.4 joules when the spring was compressed. That was the total amount of energy in the system. All of that energy got transferred into kinetic energy when the block was on the horizontal surface. All of that energy got transferred into gravitational potential as it went up the slope and stopped at the highest point. Let's do question 4. All right, we get to question 4. Same kind of question, except now in question 4 we have a ball bearing with a mass of 50 grams. We're going to convert that to kilograms. It's sitting on a vertical spring whose force constant is 120 Newton per meter. By how much must the spring be compressed so that when released the ball rises to a maximum height of 3.1 meters? So again, if we think of this, we've got a spring down here with a ball sitting on it, and it's compressed. When that spring is released, the ball is going to head up, and then it'll eventually come back down. And we know that when it gets up to here, its height is 3.1 meters above that. All right, so again, at this point here, let's call this A. At A, it only has elastic potential energy. Up here at B, it only has gravitational potential energy. And so again, conservation of energy, they must equal each other. So again, we're going to do the exact same thing we've been doing in all these questions. E total at A has to equal E total at B. At A, we only have elastic. At B, we only have gravitational. Elastic energy is 1/2 kx squared. Gravitational is mgh. 1/2 times 120 times x squared equals 9.8 times, I messed this up, that's okay, 9.8, and the mass was, what was the mass? 0.5, no, it was 50 grams, so 0.05 kilograms. And it went to a height of 3.1 meters. Okay, rearrange this, solve for x. You will get an x equal to 0.16 meters. That's it. It's as simple as that. Again, recognize what type of energy you have at each point, and then make them equal to each other, because energy has to be conserved. All right, we've got one more question. We'll head over to the other board. Question 5. So question 5, I'll read it to you. You have it in front of you there if you want, but here we go. A bullet speed may be determined by firing it into a sandbag pendulum and measuring the vertical height to which the pendulum rises. And again, there was a diagram on your paper. So question A says simply, what is the change in gravitational potential energy of the sandbag during the swing? Well, again, we have a sandbag, so we can draw it out real simple here. We have a sandbag at the end of a pendulum, and that's going to end up here, and it tells us that that is a height difference of 0.04 meters. All right, so from here to here is 0.04 meters. If we take this as our 0 line, the change in potential energy, in gravitational potential energy, is what's lifting that bag 0.04 meters. So for part A, simply have to do gravitational energy is mgh. And so we have a 10 kilogram a 10.02 kilogram block. 0.2 comes from the bullet that is in the bag, right? So because there's a bullet in the bag, we have to take that into account. 9.8 newtons per kilogram, and it has raised to a height of 0.04 meters. And if we punch that into a calculator, we will get a gravitational potential energy of 3.9 joules. Okay, so that's part A. Okay, just finding the gravitational potential energy. Part B to this question says, what is the velocity of the sandbag bullet combination at the start of the swing? Well, again, if we look at this here, we look at point A and point B. At A, it is at that point when it's starting to swing, it's only going to have kinetic energy. At point B here, it's only going to have gravitational energy. So again, conservation of energy, we're going to put those two together. E total at A has to equal E total at B. We have kinetic energy when it starts moving. We have gravitational energy when it gets to its highest point. We know what that number is already. And so we'll simply make this 1/2 mv squared equals 3.9 joules. And we have a half of our mass. 10.02 kilograms is the velocity that we're solving for. And if we punch this into our calculators, we will get 0.88 meters per second. Just like that. All right, to do part C. Now part C says, what is the original velocity of the bullet? So now what we've got is we've got a bullet over here that is heading into this block, and we want to figure out what its velocity is. Now there's a couple of ways you can do this. I think personally the easiest way is to go back and use momentum. We learned about momentum on our previous unit, and this is a classic conservation of momentum question. We have a bullet that has momentum moving into another block, colliding with another block, sticking to it, sticking inside of it, and then finding the after velocity. So to do that, we're going to, I'm just going to erase this. You've had long enough to look at it. Now we're going to look at momentum. So we're going to go P total has to equal P total prime. So on the before side, we have the bullet with its velocity. We have the bag with its velocity, which is 0. And then after the collision, the bullet and the bag stick together, and we have an after velocity. Now we already know the after velocity, that's what we figured out in part B. So when we do this now, our M1 is our 20-gram bullet, and so we have 0.02 kilograms times the velocity that we want to find, plus the mass of the bag, times its velocity, which is 0, and that will equal the combined mass times the velocity we just found of 0.88. Okay, and again, we only have one unknown here, which is our V1, and so we can solve for it. Punch this into our calculator, you will get 441 meters per second. Okay, now again, that's not the exact answer, that's in your textbook. Textbook again will use proper significant digits. I have not used proper significant digits, and so we're getting these numbers, which are just slightly off from the ones in the textbook. All right, and that's how you do it. Part D asks about elastic and inelastic collisions. I'm going to not explain that right now. I'm going to talk about that in a few days when we get to collisions. And so we'll leave it at that for today. You can find your assignment for tomorrow on Connect, or for today on Connect, that we want to go over tomorrow. And so check there. It'll be a series of questions again, not many, just a few more practice questions to get a little bit better at this, and before we move on to the next part of this. Hope you have a great day. We'll see you tomorrow.